Okay, so we want to talk a little bit about series, and some of the stuff going forward will be sort of concerned with series and how they interact with integrals. So before we get to series, we have to talk a little bit about sequences. So a sequence is just a function from the natural numbers into C, and usually we write it as Z sub n, right, instead of using the functional notation. And we usually identify sequences with an image in the complex plane, speaking of the sequence Z1, Z2, Z3, dot, 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 up to Zn. So a sequence converges. Here's a whole string of symbols. What are these strings? What do these symbols mean? So this is defining the notation limit as n goes to infinity of z to the n equals L. And you can think of it one of two ways. So if I have a sequence, there is some number L, so that for every epsilon greater than 0, there's some natural numbers greater than 0. So that for every number bigger than n, we think about this as being the distance between Zn and L is less than epsilon. Okay, so there's some number L, complex number, so that no matter what epsilon you pick, at some point, all of your points are within epsilon of L. Or you can think of it as a disk definition, right? Which is, I often think about it. I've got some point L, and if I pick out some epsilon, then, you know, my sequence Z1, Z2, whatever, my sequence wanders around a lot and might wander into epsilon and then leave, but eventually it wanders into epsilon and stays. Excuse me. If I make epsilon smaller, right, so there's some capital N, so that after I get past n, like say n is 3000, every other term of the sequence is within that epsilon. If I make epsilon smaller, then at some point, there's some n, so that all my terms of my sequence are within this smaller epsilon of n. So that's basically the idea of it. At some point, the entire tail end of your sequence is within epsilon of n. And as you make epsilon smaller, the capital N will get bigger, but everything will still be, the tail end will always be within an epsilon. So, and we say that it diverges if it does not converge. So a nice theorem is, and kind of an obvious one, is that a complex sequence converges if only if the real and imaginary parts converge. So if Zn is this sequence in the complex plane and Zn has a limit is L, then the real part of Zn and the imaginary part of Zn converge to the real part of L and the imaginary part of L. And I'm just going to actually draw a picture of this up here. Here's my point L. This is the limit of the sequence, and I have a sequence that wanders around, and if I pick a particular epsilon around L, that's my epsilon, my sequence gets inside of there and stays there. So for each of these points, right, it's got a real point part and an imaginary part. This point has got a real part and imaginary part. This point has got a real part and an imaginary part. I guess I'm doing the imaginary parts first, an imaginary part and a real part. So L itself has got what I'm calling, that's the imaginary part of L is on the y-axis. So the imaginary part of L is here, and the real part of L is down here. And that's a range of epsilon. And then we can also draw another range of epsilon for imaginary part of L. So what are we saying? Well, if our points end up within epsilon of L, then the imaginary parts and the real parts have to be within epsilon of the real part and the imaginary part of L. So if a complex sequence converges, then its two components, the real part and the imaginary part, also have to converge to the real and imaginary parts of the limit. On the other hand, this is a little bit trickier. If I have two sequences in the real line, x's and y's, and the x's converge to something and the y's converge to something, then the complex sequence xn plus iyn converges to something. So here we've got a limit L sub x, and we have lots of x's on our x-axis, and they converge to L sub x. Here's an L sub y. We have lots of y sub n's on our y-axis, and they converge to L sub y. What does it mean to converge? There's some epsilon. Well, given any epsilon, then there's a distance, L sub y plus or minus epsilon, and there's a capital letter N so that the entire tail end of the sequence is within there. So we call L equal to Lx plus I sub Ly, and then there's points that have that correspond to having the sequence whose points correspond to having a y sub n and x sub n. Do they converge to L? So to prove that, we have to say, well, if I pick any particular epsilon around L, is there some capital N so that past that, for all n, little n bigger than that, capital N, the tail end of the sequence is in there. And we know that if it converges, then for a particular epsilon, right, all the tail end of the sequences are within epsilon of Ly and Lx. But that actually it's a bad drawing, but it's actually a box, right? And so if L sub y, if we have a y sub n here and an x sub n here, x sub n is within epsilon of Lx, y sub n is within epsilon of L sub y, but x sub n plus I y sub n would be out here, and that's outside of epsilon from capital L. So we have to be a little bit careful about here and actually do an epsilon over 2. Okay, and then the epsilon of 2 would give us a little box inside that epsilon. And so that's what the exploration was going to be. So the proof, so given the epsilon greater than 0, there's an n so that if n is bigger than n, Zn minus L is less than epsilon. But we can use the triangle inequality to show that the real parts and the imaginary parts also have to be less than epsilon, and so we have the convergence. But to go the other way, we have to actually say, pick an epsilon greater than 0 so that if n1 is bigger than, if n is bigger than n1, n is bigger than n2, we have these things. So my xn's are with an epsilon of 2 of Lx, my y-n's are with an epsilon 2 of Ly. Then what's the distance between the sequence Zn and the thing that I want to be the limit? Well, the distance, remember, when we think about modulus, we think about that as distance. This has got to be less than or equal to that, which is the triangle inequality again. That's epsilon over 2, that's epsilon over 2. Add them together, you get it less than epsilon. So it actually works. So here's an example. And this example is pointing out, the moral of this example is that polar coordinates are tricky, and we've seen this about like a billion times. So Z sub n is this. So if we look at our sequence Z sub n, and we say, okay, well, z sub n minus 1, this can be made as small as we want. So, given epsilon greater than 0, right, choose capital N so that 1 over n squared is less than epsilon, right? So epsilon is some number. You can find an integer so that 1 over that integer squared is less than epsilon. Then if n is bigger than n, we have 1 over little n squared is less than 1 over n squared, capital N squared, and that's all less than epsilon. So what we've shown is that if you pick any epsilon greater than 0, you can find an integer, capital N, so that if you pick any number bigger than capital N, this number is less than epsilon. And what is this number, after all? This is the distance between z sub n and minus 1, right? Because that's what this is. So what have we shown here? Given any epsilon greater than 0, we can choose a capital N so that 1 over n squared is less than epsilon, which means that the entire tail end of the sequence is within epsilon of minus 1, but that tells us that minus 1 is the limit. Great, so it converges, and it converges to minus 1. And this isn't a big surprise. If you make n big, this gets small and it eventually goes to 0. If you rewrite this in polar coordinates, however, it gets a little messier. Right, as we've seen, Zn minus 1 in the absolute value is what? It's 1 over n squared, right? So right, the modulus of Zn actually goes to 1. So that's not too hard to show as n goes to infinity. What about the angles? What's the argument of z sub n? And this is where our problem with polar coordinates comes in, of course. Because that can be one of two things. If n is even, Zn is minus 1 plus I over n squared, because the minus 1 to the n becomes positive. So for n even, z sub n is up here. And that tells me that the argument of z sub n is, as n goes to infinity, it's going to go to pi. Because as n goes to infinity, we work our way down from above for even n. If n is odd, though, z sub n is minus 1 minus I over n squared. That means we have points down below the x-axis. And so what does that tell me about argument of z sub n? It's going to minus pi. And these should be capital A's, not little a's. So does that converge in polar coordinates? Well, the sequence converges to a point, but the polar coordinates don't seem to do that. So you have to be careful in polar coordinates. We can't say that because the sequence converges, its argument will converge, because the argument might do something goofy if you're at a branch cut. So that's a thing to keep in mind. So that's a little bit about sequences. So sequences converge. It means pretty much what you expect it to be. So a series then is denoted by this kind of thing. And we interpret that as z0 plus z1 plus z2 plus ... It's not actually adding things together. This is just a useful notation for thinking about it. This is symbolism, but we don't actually add things together because you can't add things together infinitely often. Oops, typo there. Generally, our sequences start at k equals 0, not k equals 1. So the partial sums of a sequence, now these are actually adding things together, right? You can add up the first n+1 terms. So S sub n is as z0 plus z1 plus z2 up to z sub n. Now a series converges to a limit capital S if the sequence of partial sums converges to S. So if limit as n goes to infinity of the partial sums equals something, then we say that the series is equal to whatever the partial sums add up to. The remainders, if you have a convergent sequence, you can define the remainders to be the sum minus the partial sums, so that gives you the remainders. And a complex series is absolute convergent when the sum of absolute values converges as a real series, right? And you remember a real series from complex. So things about series whose proofs I will try to put up in another video because there's a lot of sort of details in that, and I want to get through sort of the basic ideas here. So a series converges, like we proved above. Series converges if and only if its real and imaginary parts converge, but always be careful about polar coordinates. Series converges does not necessarily mean that the arguments converge. If a series converges, then the limit of the terms has to equal 0. They have to get smaller and smaller, but there's no similar statements about arguments. If a series converges, then they're bounded. All the terms are bounded, right? And if that comes from this statement, right? If these go to 0, then you can pick the biggest one in the entire sequence, and that will be the maximum. If a series converges, its remainders go to 0, and if a series is absolutely convergent, then it converges. So that's kind of nice, that last one. Again, it's sort of saying that convergence is a lot more dependent on distance than it is on argument, because the absolute convergence just depends on the modulus of things. Great, so it's a power series. So a power series is a series that looks like this. The AK and the Z0 fixed complex numbers, and Z is a variable. So our previous definition of series had the ZKs as just complex numbers. If you pick a particular value for Z, right, and plug it in, then you get a series like in the previous definition. So power series is a way to think about an infinite collection of series. Each Z in the complex plane, you can plug it in, and then you can ask yourself, for that particular Z, does this series converge or not? And you look at the partial sums and sequence of partial sums and see what you get. And so basically it becomes, for which values of Z does it converge? And if it converges, right, if this converges, then it converges to some limit S once you pick this Z, and so you can define a function f of Z, which is defined by the power series. And the flip side of this question is given a function, can you find a power series that converges for it? Right? Or given some function, can you find the power series? And the answer is usually yes, because that's what Taylor series do for us, but there are complications for that. So here's the classic, I think this is called the binomial theorem. What's the sum from k equals 0 to infinity of z to the k? And here we'll need a fact. 1 plus z squared plus z cubed plus ... plus z sub n is equal to z to the n plus 1 minus 1 over z minus 1. And you can prove that pretty quickly by multiplying both sides by z minus 1 and seeing the whole cancellation happen. Okay, so how do we show that this converges? How do we show that these are equal? To show that's equal is asking, show that right? We have to show that that converges. What does it mean for this to converge? It means look at the partial sums. And the partial sums are exactly this. So that's my S sub n. And I want to show that the partial sums actually converge to this thing. So we'll rewrite this as S sub n minus 1 over 1 minus z. And our goal is to show that this goes to 0. And if you do the subtraction, what does it become? Well, it becomes z to the n plus 1 over z minus 1 minus so z to the n plus 1 over z minus 1. And unfortunately, I've got my denominator backwards, so I'm going to have to fix that in a second. So z to the n plus 1 over z minus 1 minus 1 over z minus 1. So those two terms are this, just broken into two fractions. Oh, and I don't have another minus 1. I just have one minus sign. Minus 1 over 1 minus z. Okay. So what do I get here? I've got z to the n plus 1 over 1 minus z over z minus 1. And then these two terms cancel out because this is the negative of that. And so I could rewrite this as plus 1 over 1 minus z minus 1 over 1 minus z. Great. And this is what we're looking for, is the limit as n goes to infinity of Sn minus that. And that's going to be 0 because if we fix z, this limit is only concerned with what happens for z to the n. And if the modulus of z is less than 1, then z to the n goes to 0 as n goes to infinity. Great. And so that gives us our proof that this thing is the limit of this sequence, and so the sum is actually 1 over 1 minus z. And that would be really important. And I don't have a huge amount of space. I don't know why I thought I could answer all these questions in this space. So I'll just make a brief gesture about what happens if modulus z is bigger than 1. So if z equals 2, for example, right, we get 1 plus 2 squared plus 2 to the 4th plus dot, dot, dot. And you can see that your partial sums will diverge. If z equals 2i, you'd get 1 plus 2i plus 2i squared, right, which is minus 4, plus 2i cubed, which is minus 8, plus, and now we get 2 to the 16th plus dot, 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 minus 8i. And so this is actually going to diverge, right? But you diverge because we're going to be adding, subtracting, and then adding. We'll always be adding a bigger thing. And the imaginary parts also will diverge as well. So it'll diverge, but you have to take into account the real and imaginary parts. Okay, so Taylor's theorem. And again, we're just going to state this and not really prove it in this video. F of z is analytic in a particular ball. So I have some point z0, some radius r0, everywhere in here, f of z is analytic. Then we can actually get Taylor's theorem, right? F of z equals this power series. And this is the definition. You've seen this back in Calculus 2. And this is how you can write out the first few terms, right? First derivative at z0, second derivative at z0 divided by 2 factorial, etc. It's a pretty strong theorem because all you need is that it's analytic on a disk, and that's it. And that gives you the Taylor series. So what's the radius convergence? Well, keep making R0 bigger and bigger and bigger until you hit a point where the function isn't analytic. And that's the biggest R0 you can get. So the radius of convergence is the distance from the center of the disk to the nearest point where the function is not analytic. And then there's a bunch of stuff about Taylor series, whose proofs will be presented in another video, the proof of Taylor's theorems, the uniqueness of Taylor series, right? If you do a Taylor series, you get, no matter how you get the Taylor series, you're sure to get the Taylor series. So this is very useful, right? Existence and uniqueness theorems are really useful because however we find a series, it's the Taylor series. There's only one Taylor series, so if you can come up with a series, right, that looks like a Taylor series, it must be the Taylor series. You can integrate and differentiate Taylor series, you can substitute into Taylor series, and you can do an arithmetic of Taylor series on their common domain. So here are the basic Taylor series that you probably saw back in Calculus 2. These worked for complex numbers as well, e to the z, cosine z, sine z. So here the radius of convergence is all complex numbers. Here it's just complex numbers less than 1. And the big question is, we want to be able to find Taylor series for various functions without grinding through this formula, because grinding through that formula is tedious. So how do we find the Taylor series for f of z equals sine z over 1 minus z centered at z 0 equals 0? Well, sine z times 1 over 1 minus z, that's the function we're looking at. Sine of z. What's our Taylor series? Well, we'll just write them down. Sine is z minus z cubed over 3 factorial plus z to the 5 over 5 factorial minus dot dot dot. 1 over 1 minus z is 1 plus z squared plus z cubed plus dot dot dot. Sine z converges for all values of z. 1 over 1 minus z only converges for values of z that are whose modulus is less than 1. So this multiplication only works for z, modulus of z less than 1. Okay? So, but you can do the multiplication as long as you keep z less than 1. Whenever you do your Taylor series, keep the radius of convergence in mind. So what is this if we multiply it out? Well, you have to be a little bit careful. Are there any constant terms? No, but you can have a linear term, z times 1. That's z. Can you get any z squared terms? Sure, z times z will give me a z squared term. What about z cubed terms? Z cubed over 3 factorial times 1. That would give me a minus 1 over 3 factorial. And then z times z squared. That would give me a 1z cubed. Can I get any z to the 4th terms? Well, if I take a z times a z cubed, that gives me a z, 1z to the 4th. If I take a z cubed, this term, times a z, that gets me a z to the 4th minus 1 over 3 factorial. Plus, and then you try and group together z to the 5th, et cetera, et cetera, et cetera. And you can write out the first few terms. There might be a closed form for this or a nice summation notation thing, but I generally don't worry about that very much. Keep in mind that 1 over 3 factorial is 1 over 1 times 2 times 3, because that's what 3 factorial is. So that's 1 over 6, which is why I've got these 5/6 here. Okay, so you can multiply them together. You just have, it's just tedious, right? And it only works as long as you're on the same, if the Taylor series are defined on the same radius. What about the 3z squared over z minus 1 cubed centered at z 0 equals 0? The radius of convergence, again, this function is analytic everywhere in the plane except at z equals 1. So my center is 0, not analytic at z equals 1. The distance from here to here is 1, so that tells me my radius of convergence. Okay, so we have a series that talks about z minus 1, and I should actually it's a little more convenient actually to do 1 minus z cubed rather than z minus 1 cubed. So what's the Taylor series for this? Well, keep in mind that the derivative of 1 over 1 minus z, you differentiate that. This is 1 minus z to the minus 1. So what's the derivative? It's minus 1 times 1 minus z to the minus 2 times minus 1, right? So this minus 1 comes from differentiating the power. That's where the minus 2 is. This minus 1 comes from the chain rule in there. So the derivative of 1 over 1 minus z is 1 over 1 minus z squared. And then if you take the second derivative of 1 over 1 minus z, you'll get that to be 2 over 1 minus z cubed, right? And it's not too hard. So how can we find a Taylor series for this thing? Well, we'll start with 1 over 1 minus z is 1 plus z squared plus dot 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 for modulus of z less than 1. The derivative of 1 over 1 minus z is 1 over 1 minus z squared. And the derivative of the right side is, well, derivative of 1 is 0, then we get 1 plus 2z. Next term would be a z cubed, so plus 3z squared for modulus of z less than 1. So 1 over 1 minus z cubed, 2 over 1 minus z cubed, right, which is what we get when you do the second derivative. That would be the second derivative of the right side. Derivative of 1 is 0, derivative of 2 is 2, derivative of 3z squared is 6z. The next term would be a z to the fourth. That's been differentiated twice, so that would be 12z cubed plus dot dot dot. There should be a plus dot 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 here. Modulus of z is less than 1. Great. So our function is 3z squared over 1 minus z cubed. So what would that be? Multiply the top and bottom. No, multiply this by 3z squared and divide it by 2. So 3z squared over 1 minus z cubed will be, so if we divide it by 2, all this becomes 1, and this becomes 3, and that becomes 6. So we get 3z squared plus 9z cubed plus 18z to the fourth plus dot dot dot, modulus of z less than 1. So if we recognize this as being the second derivative, right, 1 minus z cubed is the second derivative of 1 over 1 minus z, then we can find the expansion for this by differentiating twice and then multiplying by 3z squared over 2 to cancel this 2 and get the 3z squared in there. So you can differentiate, so that's not too bad. How do you find the Taylor series for that thing? Well, we know that the Taylor series for 1 over 1 minus z is 1 plus z squared plus dot 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 for modulus of z less than 1. Okay, I should answer this question first. What's the radius of convergence? Center is z0 equals 0. Not analytic. Well, it's not analytic when you divide by 0. Or thirds. So where is it not analytic? It's at 4/3. What's the distance from 4/3 to 0? The distance is 4/3. So the radius of convergence is actually going to be 4/3. So that's how you find the radius of convergence. Much easier than having to do the ratio test. Find the center, find the distance, find the place where the function is not analytic, and find the distance between those 2 points. So here's that. 1/1 minus z is this. But we don't have that. We have this kind of a format. So we need to turn 1/4 minus 3z into something like this. So I need a 1. Into, I want to turn it into 1/1 minus something in here, which I'll end up calling w in the future. So 1/4 minus 3z, if I factor out the 4, becomes 1/4 times 1/1 minus 3z/4. And that's worked out pretty well, right? Because now I've got the right form. It's 1/1 minus something. So I'll set w equal to 3z/4. So I have 1/1 minus w. What do I know about 1/1 minus w? 1/1 minus w is equal to 1 plus w squared plus w cubed plus dot 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 for the modulus of w less than 1. Z, w, whatever you want to use as your variable, you know, you can use v or whatever. But it works as long as this symbol here and these symbols are the same. Great. W is that. So we'll substitute that back in. And don't forget to plug it in for the radius. And so you get that. Great. So we're almost done. The function is 1/4 times this thing. So our series would be 1/4 times 1, which is 1/4, plus 1/4 times 3z/4. Right, that is 3z/4 squared, plus 1/4 times 3z squared over 4. So we'll write that as, well, there's a couple different ways you can write that, but usually I would write it as 3 squared over 4 cubed, z squared, plus, now you can figure out the pattern. It's going to be 3 cubed over 4 to the 4th, z to the 4th, plus dot dot dot. And this thing, if you multiply both sides by 4/3, you get modulus of z less than 4/3. Great. And there's our radius of convergence. And so that's a useful check for making sure that we did things right. So if I have 1 over something looking goofy there, that's not exactly 1 minus 1 over z, I can convert it into something of the right form. I need 1 minus something in the denominator, so factor something out to get that 1, and then you can just go ahead with a series. What about e to the z centered at z0 equals I? So, not 0. That's a problem. What's the radius of convergence? Well, the radius of convergence is all z because it's e to the z. Changing the center isn't going to change that. So how do I move the center from 0 to I? We know that e to the z is 1 plus z plus 1 over 2 factorial times z squared plus 1 over 3 factorial times z cubed plus dot 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 for all z. But this is centered at we want to know centered at z0 equals I. So centered at z0 equals I means we want powers of z minus the center, right? So instead of having z squared, we want z minus I squared. Instead of having z cubed, we want z minus I cubed, et cetera, et cetera. So how can I go about doing that? Well, a very useful trick, and this really relies on the fact that Taylor series are unique, is we can shift the center by adding and subtracting the center from the variable. So e to the z is the same thing as e to the z plus I minus I, right? And there's our z minus I. It's e to the I times e to the z minus I. Great, so I'm gonna look at this term and I'll say, okay, set w equal to z minus I. Then e to the w is equal to what? 1 plus w plus 1 over 2 factorial w squared plus 1 over 3 factorial w cubed plus dot 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 all w. So substitute back in, what that tells me is that e to the z minus I is equal to 1 plus z minus I plus 1 over 2 factorial z minus I squared plus 1 over 3 factorial z minus I cubed plus dot 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 for all z minus I. But every point in the plane can be written as z minus I. So this is equivalent, all of these things is equivalent to all of z. So e to the z is the function I'm after, not e to the z minus I, but that's equal to e to the I times e to the z minus I. And this is just a constant. In fact, it's cosine 1 plus I sine 1. So e to the I plus e to the I z minus I plus 1 over 2 factorial z minus I, oops, I forgot my e to the I squared plus e to the I over 3 factorial z minus I cubed plus dot 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 all z. Great, so now we have a series of e to the z in powers of z minus I. That's the Taylor series because there's only one Taylor series and we've produced a Taylor series. So ta-da, there's our Taylor series at z minus I. And that's not entirely surprising. All the derivatives of e to the z are e to the I, so our coefficients are that. So that's not too bad. But this is a really useful method for finding these things. But it really depends on your series, whatever function you're playing with, playing nicely with addition. Sine does, e to the z does. So radius of convergence is going to be all z because sine is Taylor series for sine z, convergence for all z. We want to find the center at z0 equals 2. So sine of z equals sine of z minus 2 plus 2 equals sine of z minus 2 times sine of, oh, sine is sine cosine. Sorry, got to back up a bit. Cosine of 2 plus sine of 2 cosine of z minus 2, right? And this is the trig identity, right? Sum of sine of a plus b is sine of a cosine b plus sine of b cosine a. Great. So usually up above, I've done a formal substitution. W equals this, but we can just say this is going to be cosine of 2. That's this term times z minus 2 plus 1 over 3 factorial z minus 2 cubed minus plus 1 over 5 factorial z minus 2 to the 5th, plus dot, 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 plus sine of 2 times, now you get the cosine of the series for cosine, but with z minus 2 plugged in, 1 plus minus 1 over 2 factorial z minus 2 squared plus 1 over 4 factorial z minus 2 to the 4th plus dot, dot, dot. You know, then you can combine terms and see what you get. But we've shifted the center from sine from 0 to 2 because sine you can add and subtract nicely with it. So that gives us that Taylor series. Okay. And the convergence is going to be all z. I'm not going to go through that much more great detail because I'm more interested in rational functions. What's the Taylor series for f of z equals 1 over 1 minus z centered at z0 equals minus 1 minus I, and what is its radius of convergence? So we'll do the radius of convergence first. The center is minus 1 minus I, that's down here. There's our center for our Taylor series. And the singularity, right, not analytic, is at 1. Because if you plug in z equals 1 into 1 over 1 minus z, this is equal to 0 on the bottom, and so you're dividing by 0, not analytic. So we want to know what's this distance. But, you know, that's just Pythagoras' theorem, right? This is 1, this is 2. So this distance is the square root of 5. So our radius of convergence should be square root of 5. And hopefully that'll drop out at the end because we always have to substitute in for the radius of convergence of this. So how do we find the Taylor series for this if we want to shift the center? We'll add and subtract the center from z. So that's our, that's what we've done, added and subtracted that. We haven't changed anything, so because this is all just adds up to 0, so it's 1 over 1 minus z. So I get a little confused by minus signs. So what I want in the bottom is 1 minus the quantity z minus 1 minus I. Lots of minus signs, we have to be careful about them. So this is the variable, and this is the center. So it should be z minus the center. That's what we're always trying to do. So which of these terms over here actually help me figure that out? So if we actually distribute this, I want 1 minus z plus 1 plus I. And that's actually 1 minus z minus 1 minus I. So that means this part. So this is equal to 1 over 1 minus z. And I can regroup that as 1 over this whole part now. That's this. So I've got 1 minus z minus the center. And then I have this plus 1 plus I floating around. So I need to deal with that. So what I really have is 1 over 2 plus I minus z minus the center. Ugh. So, but we can do the same trick we did with the 4 above. We can factor out the 2 plus I. And then what have we got? We've got 1 over 1 minus z minus the center over 2 plus I. Put a parentheses around that very carefully. Awesome. So we're in good shape now because we can just do what we did above. We can set W, because we've got 1 over 1 minus something. So we'll make W equal to the something, Z minus 1 minus I over 2 plus I. And then we know that 1 over 1 minus W is equal to what? 1 plus W squared plus W cubed plus dot, dot, dot for modulus of W less than 1. Okay. Great, so there's our 1 over 1 minus W. So what we'll do then is we plug back in for W. Z minus the center over 2 plus I is equal to 1 plus 1 over 2 plus I. That's an I. Z minus 1 minus I. God, so many parentheses. Plus, and now W squared will be 1 over 2 plus I squared, right? Because that's that. And then Z minus the center, quantity squared, plus more terms. That's just expanding this part. Great. So, have we done yet? No, we haven't. We want 1 over 1 minus Z. We've got this part done. But to get 1 over 1 minus Z, we have to multiply everything by 2 plus I. So 1 over 1 minus Z is equal to 1 over 2 plus I times this thing. And then remember that Z minus the center over 2 plus I. And so I'll take my 1, basically means taking the 1 over 2 plus I and multiplying it through this. So we get 1 over 2 plus I plus 1 over 2 plus I squared times Z minus the center plus 1 over 2 plus I cubed times Z minus the center, etc. And so often when you watch professors do this, when they realize they make a mistake, they'll try and cover it and say, gosh, what did I leave out that we ought to have done? But I just forgot it. I didn't leave it out for any kind of tricky reason. Keep track of your radius of convergence. I forgot to put it in here. I forgot to put it in here. But its modulus of W is less than 1. So we want Z minus the center over 2 plus I to be less than 1, which means that we want Z minus the center in modulus to be less than or equal to the modulus of 2 plus I. And if you grind that out, it is, and it's not less than or equal to, it's strictly less than square root of 5, which is what we got at the beginning. So don't be like me and forget to deal with your radius of convergence. Great. So it is kind of looking like a lot of algebra, but remember that it's just, this is my center, and I always want Z minus my center and expand in that. And so this gets us our Taylor series. Now, can we find a Taylor series centered at -1 minus I, but valid for large Z, right? And then notice I'm not actually, I shouldn't have used the word Taylor series. Not using the word Taylor series here. We just want to find a series. So we'll go back to this. So we have 1 over 1 minus Z equals 1 over 2 plus I minus, got to keep track of my parentheses, minus Z minus the center. Okay, so we had gotten to that point. And we want to know, can we get a series for large Z, for Z greater than square root of 5? And so what we'll actually do here, instead of factoring out the 2 plus I, we'll factor out the Z minus the center. So we get 1 over the quantity Z minus the center times 1 over 2 plus I over Z minus the center minus 1. So that's almost great. We will rewrite this as 1 over 1 minus Z equals, now I'm looking at this last thing, so I've got 1 over Z minus 1 minus I, that's this term, times, I'm just going to multiply the top and bottom by minus 1 there, so minus 1 over 1 minus 2 plus I over Z minus 1 minus I. Hooray. Great. Why do we want to do that? This is 1 minus something in the denominator, right? We can always just plug in a I in there. So we can rewrite this then as minus 1. I'm going to move this minus sign over to this one, over Z minus the center, times 1 over 1 minus 2 plus I over Z minus the center. And then we can do the same trick we've done before, right? Set this equal to W. So I've got a minus 1 over Z minus 1 minus I, that's this term, times, and now we'll just expand this in the Taylor series, this is W, so it'll be 1 plus W, which is 2 plus I, over Z minus 1 minus I, plus W squared, so that's 2 plus I, over Z minus 1 minus I, quantity squared, plus W cubed, 2 plus I, over Z minus 1 minus I, quantity cubed, should be an I there, plus dot, 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 and of course, whatever our W is, the 2 plus I over Z minus the center, which is minus 1 minus I, in modulus, that all has to be less than 1. Woof. Great, so here's our series. 1 over 1 minus Z is minus 1 over Z minus 1 minus I. That's this term times the 1. Then I take this coefficient out front, multiply it by this, plus 2 plus I over Z minus 1 minus I quantity squared, because I multiply this times this, and that's actually a minus sign from here. I have to keep track of that minus sign. Minus 1 times the top is a 2 plus I squared. And then the thing here times this squared, Z minus 1 minus I quantity cubed minus dot, 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 right? And then dealing with this, we want modulus of 2 plus I to be less than the distance between Z and the center. We know from above that that's square root of 5. So what this is telling me is that this sequence whatever this is, converges as long as I pick a z in the plane somewhere that's more than square root of 5 away from -1 minus I, more than away from my center. And it's not a Taylor series because all my powers are in the denominator, right? This would be actually a negative. You can think of this as being a -2 power, -3 power. Taylor series has positive powers. So that's a little bit weird. But this last example shows us that negative powers can be included in these series. And if we use negative powers, they're called Lorentz series. And so we need a little bit of a notation here before we present Lorentz series. An annulus centered at Z0 with inner radius R1 and outer radius R2 is defined that like this. What that means is I've got Z0, I've got an inner radius R1, and I've got an outer radius R2, and the annulus is the space in between, right? And if we let the inner radius go down to 0, then we're just looking at the punctured disk of radius R2, so that's the disk of radius R2, but without the center of it. And so Lorentz theorem says that if f of z is analytic on an annulus, and gamma is a curve that goes around Z0 and whose trace is entirely in the annulus, so something like that is gamma, then you can rewrite our function for everything that's in the annulus as a sum. This is sort of a Taylor series sum, positive powers, plus a series that's got negative powers, the z minus z0 and this in the bottom. And then you have these formulas, which you could recognize as being from the Cauchy integral formula. So they're related to the derivatives of f of z. These are the coefficients of Taylor series. These are the coefficients, the bk from over there. In the integral from bk, the integrand, right, is actually z minus z0 to the n minus 1. Right? So if you bring this term up to the top, it shows up with an n minus 1. So if your function is actually analytic everywhere inside of here, oops, I forgot the f here. So is f of z, so this should be f of z, z minus z naught to the n minus 1. So if your function is analytic everywhere inside the annulus, then all these coefficients are 0. So the bk's disappear and you're just left with the Taylor series, right? So what this Lorentz series allows us to do is it allows us to look for places where the function isn't analytic and take that for your center. And then you can define a series for this function away from that center. And the proof for this theorem, like the proof for Taylor's theorem, we presented in a separate video. And I think this is the last thing to do then is find Lorentz series for this series centered at Z0 in the region A001 and the region A01 come infinity. So Lorentz series are unique, so if you can, however you can find it, you can do that. So f of z is 1 over z times 1 over 1 minus z. And I can open that up as a Lorentz series z cubed plus dot 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 for modulus of z less than 1. But now we have to say also bigger than 0 because 1 over z is not defined at 0. So in the annulus centered at 0 of radius 0 and radius 1, so that's this thing. And what is that? It's 1 over z times this. And that's good for that region. So we've got a series now. It's not a Taylor series because this is z to the minus 1, and Taylor series don't have negative exponents. Lorentz series do. What about in the region 0, 1 to infinity? So what is a series for 1 over 1 minus z that converges for a modulus of z bigger than 1, right? The series we usually has convergence for modulus z less than 1. Well, we'll do the same trick we did before. We'll factor out the z. And then we'll throw in a minus sign. To get everything set up, right? So this minus sign, and if we apply this minus sign to these two terms, right, you get a minus 1 plus 1 over z. That's what we have there. Great. So 1 over 1 minus z equals minus 1 over z times 1 plus 1 over z plus 1 over z squared plus 1 over z cubed plus dot, 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 as long as the modulus of 1 over z is less than 1. Right? Multiply both sides by the modulus of z here, and you get 1 less than the modulus of z. So this series here, it's a Lorentz series, and that converges for modulus of z bigger than 1. So what's a series for this function for z's bigger than 1? Well, just multiply everything by z cubed, z to the 4th, minus 1 over z to the 5th. And that converges as long as you are outside of that. So what we've managed to do then is we have a function not defined at z equals 0 or z equals 1. And what we've done is, if this is 0 and this is 1, and this is the circle of radius 1, in this annulus, we have 1 power series. That's this one. So in here, f of z equals 1 over z plus 1 plus z plus dot, dot, dot. And then we have another series, that's this one, that holds everywhere outside of my circle of radius 1. So we can talk about this function as a series pretty much everywhere except at 0 and 1, where the function itself doesn't exist. And also on this boundary, the unit circle, because it's going to diverge there in some goofy way. So that's the basics of how do you actually find Lorentz series and Taylor series. Moving a center way up here somewhere. How do you move the center? Add and subtract the center from the variable and try and regroup things. And then you can figure out what the new series is. Because Taylor series and Lorentz series are unique, if you can get it by doing this trick, then you've got it and you can stop. Okay, so that's how to create series. And we will end this recording here.